Welcome to lecture number 8 for ECE 321 Analog Electronics. This lecture we look at filters, how poles and zeros affect the frequency response of a given filter. Now, a little background. From the previous circuits, you can build filters that have real poles, complex poles, and zeros at s equals 0. And you could do other options too with other circuits, but those are the circuits that we looked at last time. Filter design uses this to place poles and zeros to give a desired frequency response. In this lecture, we're looking at how the poles and zeros affect the gain versus frequency. Basically, how do you design a filter? So, starting out, there's analysis and design. Analysis is actually pretty straightforward. Suppose, for example, I have the following filter. This would be a second-order differential equation or an op-amp circuit with two capacitors. And the input is a sine wave. Find y of t. Well, using phasors, that's actually pretty straightforward. X is just 4 minus j5. Again, in phasor notation, the real part is cosine. The complex part is minus sine. So 4 cosine plus 5 sine has the phasor representation 4 minus j5. The frequency is j6. Again, we assume everything is in the form of e to the st. If s is 6, that's e to the 6t. What e to the 6t looks like is it blows up. E to the j6t is a cosine. j6t. That spins around the unit circle and gives you a cosine function. So s equals j6. This is the gain everywhere. All I care about is what's the gain at j6, the frequency of the input, times the input at 6 radians per second. Multiply it all out, I get a complex number. What that number means is the real part's cosine minus j is sine, and there's y of t. So circuit analysis with a single sine wave input is actually pretty straightforward. Second form, if I know the frequency of the input, I just plug in s equals j omega, find the gain of the filter at that frequency, and multiply by the input in phasor notation. Suppose you don't know the frequency of the input. Well, there's a thing called a bode plot. It's a graphical way to describe a filter. For example, suppose I have this filter. I want to know how it behaves. What I could do is calculate the gain at, in this case, 1,000 different points between 0 and 10 radians per second, and then plot them. In MATLAB, I would just set up the vector omega, your frequency, going between 0 and 10, steps of 0.01, and I made it a column vector just because I like column vectors. S is j omega, and then g of s is almost the same way you write it. It's 2s over s squared plus 2s plus 10. I have to use the dot notation. That tells MATLAB, don't treat this like a matrix. Treat it like a column of vectors, or column of numbers, and do element by element computations. We have a guest appearance by Momo. Say hi, Momo. But here we go. Momo's got to say hi. Say hi. See? Hi. Get back at the ranch. Let's see. So I've calculated g of s. G is going to be a complex number. When I plot this, I can plot the real part of G, the complex part of G, the amplitude or angle. The amplitude actually tells you something. That tells you how much the gain is. So that's typically what you plot. Sometimes you'll plot the angle, although personally I don't know what angle really tells you, so I don't use it. But amplitude tells you gain. So plot the frequency versus amplitude, and here's what you get. That tells you that this is a bandpass filter. Frequencies near DC have a very small gain. Really high frequencies have a small gain, and frequencies close to 3 radians per second get passed. So that'd be a bandpass filter. So that's analysis. Again, analysis is pretty straightforward. Design is the hard part. With design, I want to figure out where to put the poles and zeros to give some desired frequency response. In this lecture, we're going to look at how real poles affect the gain versus frequency, how complex poles affect the gain versus frequency, how zeros affect the gain versus frequency, and then using a MATLAB function called fminsearch to design a filter. So starting out, if I want to know how the poles affect the gain versus frequency, I could use this graph. Let's take the simplest case, 1 over s plus a. To find the frequency, gain versus frequency, I plug in s equals j omega. So when I find the gain of 1 over j omega plus a. Well, graphically, if I put an x at minus a, where the root to this equation is, this vector right here is plus a. This vector is j omega. So the vector from the point, from the pole to the point on the s-plane is j omega plus a. So graphically, the gain is 1 divided by this blue line, divided by the vector j omega plus a. And you kind of see that when I'm at minus a, the gain's a maximum. So let's kind of draw it sideways if this is gain. Normally gain goes up, but I'm going to draw it sideways. Right here, the gain will be maximum, 1 divided by a. As I move up and down the j omega axis, the distance to the pole stays about the same. So this stays flat. Then the distance increases and the gain drops. When this distance is a and that distance is a, I'm down by square root of 2. So this will be square root of 2 times a. That's your 3 dB down point or half power point. So what you can do with that? Yeah, let's get this out of the way. Suppose I have a complex pole, a pole at minus 1 plus j10. In that case, what's going to happen is, again, I've got my s-plane, the pole's right here at minus 1 plus j10. The gain is the distance, or 1 divided by the distance from the pole to your point s. S is j omega. As I sweep, the distance gets smaller, the gain gets bigger, and then the distance gets bigger, the gain gets smaller. So I plot the gain versus frequencies kind of going sideways. It's going to look like this. The peak, I didn't quite do that right. Peak is at the complex part of the pole. That's right here. So at 10 radians per second, the complex part, that's the maximum. The bandwidth, this distance is 1. So when I go 1 away from your pole, the distance increases by square root of 2. So when I go 1 away from the pole, right here at 9 and 11, the gain drops by square root of 2. That's your 0.707 gain frequency. So this right here is the bandwidth. Kind of arbitrarily, the bandwidth is defined as from your 3 dB down, or where the gain is 0.707 of the peak, to 0.707 of the peak. The bandwidth is 2 times the real part of the pole. And this is the imaginary part. So that kind of lets you design filters. If I want to pass certain frequencies, the imaginary part tells you what frequency you want to pass. The real part tells you what the bandwidth is. And you kind of see that in MATLAB. So for example, here I've got a pole at minus 1 plus j12, minus 1 plus j20. Plot the gain versus frequency from minus 40 to plus 40 radians per second, just so you can see the complex conjugate. And the numerator is just a constant. The denominator is s plus p1 times s plus p2 times s plus p3 times s plus p4. Plot that, and here's what you get. So notice I've got a resonance at 12 and 20 radians per second. That's the complex part of the pole. And the bandwidth, if we go 3 dB down, that's about bandwidth of 2, bandwidth of 2. If I make the real part bigger, the bandwidth gets smaller, or gets larger. So here this one just got wider. The bandwidth is now 4 radians. Go to the 3 dB down point. This width is now 4 radians. And the resonance is still 10. If I make it smaller, like 0.5, I get a more narrow filter. This has a bandwidth of 1 radian per second, plus or minus 0.5. If I shift the poles around, like let's make this go up to 30, 25 initially. The resonance at 20 shifted over to 25, the complex part of the pole. Make that 30. Resonance is now 30 radians per second. So again, the complex part of the pole is the resonance. The real part of the pole, twice the real part of the pole, is the bandwidth. So with that, if you had a gain versus frequency like this is kind of like one of the handouts, I can sit there and calculate what's the transfer function. Oh, actually, let's back up for one thing. That's for poles. If I do zeros, zeros force the gain to 0 at a certain point. So if I said the numerator is just S, and then plot it, now suddenly the gain at S equals 0 is 0. If I were to say the numerator is S plus J times 20, S minus J times 20, now at 20 radians per second, the gain is 0. So the zeros tell you where the gain is 0. The poles tell you, well, the resonance tells you the pole, the imaginary part. The bandwidth tells you the real part. So going back to this problem, if this is the gain versus frequency, what's the transfer function? Where are the poles and zeros? And we'll give you a couple minutes to think about that. Let you pause it. Okay, then picking up then, let's change the color a little bit. Right here, actually, how about right here? I know I've got in the transfer function an S in the numerator because the gain at S equals 0 is 0. I know I've got a pole at 10 radians per second, so I know I have something at 10 radians per second. And there's another resonance right here at 30 radians per second. I now have another pole at plus or minus 30 radians per second. That's the complex part. To find the real part, go down 0.707. So 0.7 times 3 is 2.1, right about here. That distance is about 4 radians per second. Half that is 2. So this one's at 2. Plus or minus J10. Take this peak, that's at 6, times 0.7 gives you 4.2. That's this distance. That distance is about 2 radians. Half of that is 1. So your pole's at minus 1 plus minus J30. Plus there's a gain on top. What you could do is pick any point you want. The poles and zeros set the shape. The amplitude is set by gain K. What I could do is calculate the maximum of this guy, or the gain at 30 radians per second. Pick K to make the gain 6.2 at that frequency. And there's my filter. Which again, kind of what this is doing. A generalized filter has poles and zeros. Again, what the zeros do is they force the gain to 0 at the 0. The poles increase the gain at the pole. So in generalized 0, I've got a gain K, zeros, and poles. Graphically, what you're doing is I've got the S-plane. I can scatter zeros over here and their conjugate. I can scatter poles around. When I'm close to a pole, the gain is large. When I'm close to a 0, the gain is small. So you place zeros by frequencies I want to block, place poles by frequencies I want to amplify or pass. That's kind of the generalized strategy for designing filters. And that's something you can kind of do by trial and error, or you can let fminsearch do it for you. So the procedure using fminsearch is I'm going to specify what the filter should behave like. So if this is my frequency versus gain, I want to filter that as a gain of 1 out to 4 radians per second, and then again a 0. That's what I want. I then specify the form of the filter. The filter is going to have a bunch of poles and zeros. So, given the poles and zeros, it's going to have some gain versus frequency. Take the difference in the two, square it, and call the sum squared error my cost. Find the filter that minimizes the sum squared error. For example, suppose this would be like a function fminsearch I could use. Suppose I want to assume the filter's in this form. I've got 4 real poles, a 0, or the numerator, no zeros. What's the best I can do? Where here's my cost function. That's what I want it to be. Gain is 1 for frequencies less than 4. Given A, B, C, D, E, here's what the filter really is. Find A, B, C, D, E to come up with the best filter possible. So again, notice I've got real poles. I want the filter to have a gain of 1 less than 4, and the actual poles. If I save that, cost F1, then in MATLAB I can sit there and guess again, try to come up with the best values of A, B, C, D, E. So that'd be, suppose I guess the numbers 1, 2, 3, 4, 5. What this did is the red line is the desired response, gain of 1 between 0 and 4. The blue line is my filter, and this is my sum squared error. Kind of see it's actually a pretty bad filter. So let's change that. Let's make this 10, 2, 3, 4, 5. A little bit better, not great. How about 100, 2, 3, 4, 5? Better. So I can guess again, or let MATLAB guess for me. And so I want to minimize the function cost F1. My initial guess is 100, 2, 3, 4, 5. Let her fly. And what MATLAB is doing is it's guessing, trying to figure out what values of A, B, C, D, E minimize J. And it's kind of fun to watch. What you're seeing is if I constrain the system to have real poles, I'm not going to get a very good filter. What's nice about real poles is it's actually really easy to implement. That would be a 4-stage RC filter with an op-amp, DC gains bigger than 1. But the net result is not a very good filter. That's real poles. So looks like it's about to come up with the answer. And that's what MATLAB will come up with. Saying the best you can do is put all 4 poles at minus 4.9165. Suppose instead, well, that's kind of what you're getting. If I plot the frequencies and the complex conjugate, the red line is what I want, past frequencies between minus J4 and plus J4. The blue line is what I got, and I put 4 poles right here. Again, I constrained it, the poles have to be real. Suppose I opened it up. Suppose I allowed the poles to become complex. In that case, I could use this as my cost function. Same thing as before. I'm going to pass A, B, C, D, E, but now I've got one set of complex poles, possibly complex. Here's the second set of complex poles. Can I do better? And kind of tell it I'm not going to do worse. So here's my cost function called cost F. I want the gain to be 1 for frequencies less than 4. And MATLAB, I can call it. So let's do cost filter And I could use random numbers, 1, 2, 3, 4, 5, and not great. I could do that. I also kind of know what the answer should look like. I probably want to pull right around -1 plus j1, another pull at -1 plus j3. So that would be -1 plus j1 would be s squared plus 2s plus 2. -1 plus j3 would be s squared plus 2s plus 10. And the numerator should be 20 for DC gain of 1. Well, that's better. Let's take the pull at -3, move in the real part. So that'd be s squared plus s plus 10. Pulls at -0.5 plus minus j3. Let's see, there's the resonance right there. Let's bring this down a little bit more. Take the pull at -1, move it out a little bit. Too much. Maybe take that second pull, reduce the resonance some, and kind of playing around with it, you can kind of move the pulls around and see what you're doing. Or let fminsearch do it for you. And that's the beauty of fminsearch. Knowing nothing about filter design, you can do a pretty good job designing filters. It helps if you give it a reasonable initial guess, but usually it works out pretty well. Sometimes it'll kick out due to a maximum number of iterations. I'll kind of show that in a sec. If your initial guess is too far off, it'll have a hard time finding it. In that case, what you can do, let it solve. I can sit there and tell it, pick up where you left off. Using the previous solution, keep going, can I do better? And kind of see that I had the solution, the sum squared error is 13.07. Let's see if I can make that smaller. Nope, that's about the best you could do. So this is the filter it came up with. That's your A, B, C, D, E. Meaning it's 36, here's your A, B, C, D, E, over S squared plus BS plus C, S squared plus DS plus E. That's the best I could do. And that's what the filter looks like. Again, plotting for negative frequency to plus frequencies. I've got a pole at -0.45 plus minus J3.49. So the complex part of the pole tells you this resonance. The bandwidth is twice the real part. There's another pole at -1.09 plus J1.41. That's this pole. Resonance is at 1.41 radians per second. The bandwidth is 2. And I have this shape. I could do 5 poles. Again, just add one other pole. Let it fly. And here's what you get. Or plotting it out, I now have 5 poles. One pole is real. It has to be real since I have an odd number. 4 other poles. Here's a resonance at DC at s equals 0. Here's another resonance. There's a third resonance. And kind of notice there's a pattern here. Those poles are on an ellipse. I scatter poles in the region of the frequencies I want to pass. And it's not completely arbitrary. These are following a fairly well-defined pattern. It's an ellipse. So there's kind of the general rule for designing filters. You scatter n poles in the region you want to pass. And for, in this case, this is a Chebyshev filter. The resonance gets bigger than 1. The poles belong on an ellipse. And we'll see that on our next lecture when we're designing Butterworth and Chebyshev filters. But the beauty of fminsearch is knowing nothing about filter design, I can do a pretty good job designing filters. In fact, you can even do some kind of strange things. Like suppose I want the gain to be 1 for frequencies less than 3, and I want it to be Again, I want the gain to be 1 out to 3 radians per second, then follow this curve. That's your 1.9 minus 1.3W for frequencies between 3 and 6. So you can see that. Come up with a filter that does that. Well, fminsearch will sit there and iterate, keep on guessing again until it does the best it can. And again, this is still with just 4 poles, 2 sets of complex conjugate poles. It's playing around with the 2 poles, trying to figure out where they belong, what's the real part, what's the complex part. So I get as close as I can to the red line. And it's not perfect, but it's actually doing pretty darn well. After some time, it'll come up with the answer. Yeah, plotting the results slows it down as well, but it's kind of fun to see. It says, this is your A, B, C, D, E. That gives you the blue line. That's the closest MATLAB can come up with for my desired filter. So in summary, for filters, we've got analysis and design. Filter analysis is actually pretty straightforward. You just plug in S equals j omega. If there's a single frequency coming in, I analyze the gain of the filter at that frequency. I use phasor representation, real parts cosine minus j as sine, plug it in and get a complex number, and that's your output. Real parts cosine minus j as sine. If I want to plot the bode plot, that would be the gain versus frequency, kind of like we're showing there. Again, MATLAB is useful. I just calculate what's the gain at 1,000 points and plot them. That's analysis. Pretty straightforward. Filter design is a little bit harder. In general, I place poles by the frequencies I want to pass. I place zeros by the frequencies I want to reject. And here we haven't been using zeros because we don't have the circuits that do complex zeros, but they do exist. And well, that's the general idea. And you can use fminsearch to optimize these. Shift them around until the gain versus frequency is close to what you want. So that's kind of the idea on filter design. Next class, we're going to look at some very specific types of filters called Butterworth, Chebyshev, and elliptic filters. But that's lecture number 8 for ECE 321, Analog Electronics.